This square represents a matrix, we'll say. Pretend it's filled with numbers. Now, I could go type numbers in there, but sometimes I just want to use my imagination because it would take too long. All right? We can take this matrix. Can we multiply it by this matrix? We can if and only if we line these things up and this area makes a perfect square. And it turns out it doesn't. Therefore, you cannot multiply these two matrices together. If you try, it throws an exception or a failure or something because you can't do it. However, if this matrix were precisely the same size as that matrix, by which I mean, when I say precisely the same size, I mean if this region is a perfect square, then you can multiply them together, right? And here's why. Because the way you multiply matrices together is you take this vector and you take that vector and you dot product them together to get that element. And the resulting matrix will have a size of exactly that size. And if we sweep through this entire space of that target matrix and we dot product the corresponding vectors of those two matrices together, we have just done matrix multiply. There, that was the graphical presentation of how to do matrix multiply. Now we'll do the empirical or the numerical example of it. Here's this unit test. This is the one we're talking about, right? Okay. Let me zoom in a little just so that's big enough to see. Everybody see that? Great. So what we're dealing with is down here we have a 1, 2, 3, 2, 1, 0. And up here we have a 0, 1, 2. Whoops. 1, 2. Can we multiply these two matrices by each other? The answer is yes, because if we line them up like that, there's a square here. Or more specifically, the rows of this matrix line up with the column, have the same size as the columns of that matrix. Therefore, we can. Okay. So we're going to compute y is equal to mx plus b. I use lowercase letters in bold font for vectors, and I use capital letters in bold font for matrices. And that isn't actually bold font. Let's pretend it is. And that's one common way to do it. Another way to notate a vector is to put one of these symbols over the vector. Have you seen that? Okay. That way looks too cluttery to me, so I like the boldface way instead. Okay, let me actually make it boldface. Y is equal to mx plus b. I shouldn't boldface my equals and my plus because that has no meaning, but this is going to be too cumbersome, so just go with it. Capital letters a matrix, lowercase is a vector today. Okay. This matrix is y. No, it's not. This matrix is m. This one is x. And what do we get if we multiply them? That's going to be 0 times 1 plus 1 times 2 plus 2 times 3, which is 2 plus 6 is 8. Do you agree? So this number right here will be an 8. And the next one down is 0 times 2 plus 1 times 1 plus 2 times 0 is 0 plus 1 plus 0 is 1. So this should be a 1. Therefore, we have concluded that m times x is the vector 8, 1. Everybody agree? So this vector I will call mx. Okay, now I have this vector called b somewhere. What's b? 8, 1? 8, 1. It's the same number. That's got to be my typo. I copied mx into where b was supposed to be instead of whatever b was supposed to be. I think I wanted b to be 1, 5. Ha ha ha. If b were 1, 5, then this unit test would be correct and the answer would be 9, 6. Everybody agree? Well, you found my bug. As is, it's going to be 16, 2. And so either b is incorrect or the answer, mx plus b, is incorrect. So whichever one you want to fix, go ahead and fix it, and now your unit test is valid. And my test is broken, and I apologize.
I have another question on this assignment. So in the Java example, the starter code has a size t thing, but I think that's just a C++ thing. Size t's.
Oh yeah, C doesn't. That is a C++ thing. I think you're right. So you're doing it in C rather than C++. Oh, there's a size t in a Java example somewhere?
Yeah, in the first example. In the first example code, like that in 3 or something.
All right.
It's down in this one.
I'll just search for size t. C++ example. Okay. This is very embarrassing, but this is how my bugs get fixed. Web 2018 Spring A1 K instructions. Okay, B, we decided, remind me, what was B supposed to be? 1, 5? One issue fixed. This is called real-time bug fixing. Java example, that better be an int, and this better be an int too. And shame on me for not doing more testing. I run a prepared script. I refresh my page. And there's the int. There's the 1, 5. Problem solved. Yes?
Similar question. So in the C++ version, in the tensor class, there's a sign size sheet.
Ah, another one?
And that's object stuff, so it doesn't compile the windows. Is there an easy way to just change that in as well?
Ah, good point. Okay, this is in the C++ toolkit. We're going to be looking at this today, so this will give us a good chance to dig into here. In the source code, go into there. That's not awesome. Okay, well, let's do this properly. How about, I'm going to go through this code today, and when I get to that bug, will you point it out for me, and I'll find a good solution for you. But for right now, unit test is fixed, instructions are fixed, and I've just successfully demonstrated how to do matrix vector multiply, right? Okay, how would you do matrix multiply? Same thing, it's just this thing would be wider. Why do people even use vectors? Isn't a vector just a column matrix, or is it a row matrix? That's why they use vectors, is they don't want to specify. A vector is a matrix that either has one row or one column, and basically you transpose it whenever you need to, such that it just works. Otherwise, a vector is a one column, one row matrix. Is that a good way to think about it? Okay. Now that you can do matrix vector multiply, actually let me just point out, do you believe that matrix multiply is a generalization of regular multiply? Is it? Since we're considering math, I think we should look at some of the properties. Here's one of the reasons people say it's not. If you take 5 times 7, what do you get? 35. If you take 7 times 5, what do you get? 35. In other words, multiplication is, what's that property? Reflexive, commutative, transitive, commutative? Okay, we'll say that one's commutative. We know we can multiply these two matrices together because we did. By these two matrices, I mean the only two that still remain on the screen, right? But you cannot multiply that one times this one, because if you try, see how they don't line up? And how do you compute the dot products? of this thing with that, a vector of size 2 with a vector of size 1. You can't dot product them. Therefore, you can't multiply these matrices. Therefore, matrix multiply is not commutative, and yet scalar multiply is commutative. Different properties, therefore one's not a generalization of the other, right? I claim matrix multiply is a generalization of scalar multiply. Here's why. What we really did right here is we didn't do 7 times 5. We did 7 times 5 transpose. And actually we transposed the 7 and then we transposed that too. Now, what happens if you transpose a scalar? It's a matrix, it's a 1-by-1 matrix. If you transpose it, it's the same dumb thing, right? Well, it turns out that if we transpose this matrix, it, let's see.
I don't think it works that way.
That's not going to work.
1 by 3 and 2 by 3.
I guess I have to write it out this way. 0, 1, 2. Now if I transpose this matrix, I've got a, what is it? 1, 2, 2, 1, 3, 0. And now we do the multiply. 1 times 0 plus 2 times 1 plus 3 times 2 is 8. And then 2 times 0 plus 1 times 1 plus 2 times 0 is 1, which is the exact same result except transposed that we got when we did it before. Do you remember that? So if we transpose this thing, then it turns out it's the same. So to put that more formally, if we put a t right there and a t right here and right here. Move that part right back there. Clean up a little. Okay. Those t's mean absolutely nothing because we're in scalar land, but really they kind of should be there, because if they are there, then scalar arithmetic works exactly the same as matrix or linear algebra arithmetic, and that makes us feel good because now everything, we have a perfect multidimensional generalization of scalar algebra. Doesn't that make you feel better? Turns out matrix multiply is a generalization of regular multiply. It's just you didn't know you were transposing your scalars all along. Okay, there's a way of looking at it. I like to look at it that way because now we're starting to realize you can operate in multidimensional space just as well as you can operate in the one-dimensional space that you're very comfortable working with. In other words, your horizons have just been expanded. All the math you know, everything you've ever done should work just as well in n-dimensional space, and that's kind of important, especially when you're doing machine learning. Okay, why is hyperdimensions important in machine learning? Lots of features. Yeah, that's pretty much the answer. Let's give an example. Let's see. Optical pathway. A human... that's not the one I want. Let's see, how about retina? I'm looking for the number of retinal cells on the eye. I'm sure it'll be in here somewhere. It's probably in the... The entire retina contains about 7 million cones and 75 to 150 million rods. There you go. You're right, I should have just typed the question into Google. It would have just answered me, huh? Okay. In other words, as you walk around through your lives, every moment that you see something, so if you just open your eyes for just a split second and then close them again, there were 75 to 150 million numbers, and I'm putting numbers in air quotes because they're not really numbers, but they're signals. A large number of retinal cells are in the back of your eye, and all of those numbers were sent through this big fat cable called your optical pathway, and it travels from your eyes all the way to the back of your brain, so it can process the information. Why do they process the information in the back of your brain instead of right up next to your eyes? I don't know either. But there's a lot of numbers going in there. Have you ever wondered why you can look at a face and say instantly, that's my mom, or that is not my mother, right? I wasn't pointing at anyone, by the way. I was just kind of, my eyes are blurred. I have bad vision anyway, so if I ever point at somebody, I'm not pointing at you. Why do we know so instantly? Because you have a lot of numbers, and none of them are really enough to tell whether it's your mom or not, right? Because, I mean, seriously, if you only had one pixel, should it be dark or not dark? Is this you zoomed into a picture, is that a picture of your mom? I don't know, because that's just not enough to tell. But if I had enough dots, I mean, I could sit here and spray paint a picture, and eventually it would look like my mom. Well, I'm going to get in trouble if I keep doing that. That doesn't look like my mom. But given enough dots, at some point it becomes absolutely clear to you that what you're seeing is or is not what you expect or imagine it to be, correct? This is an example of, you took a vector. In fact, that vector has a size of maybe 150 million. Now, truthfully, it's not that big because some of the retinal cells, the rods, are not responding. Some of them are probably not used. It's going to be smaller than that. Plus, there's a lot of dimensionality reduction that occurs before the optic pathway connects to your visual cortex. The number is about 100 times smaller anyway. But using that many numbers, you get a picture. And based on that picture, you're easily able to tell yes is or no isn't, right? If you were trying to recognize Osama bin Laden in football stadium pictures, could we do it? Well, if your camera has enough pixels, that provides a lot of numbers. If it doesn't, then probably not, okay? So the task we have in machine learning is often, I close my window. There it is. We've got a model. This box